In the next section, we're going to be talking about how angle measures can affect side lengths of right triangles. Okay? Up to this point, we've never actually looked at angle measures of triangles other than maybe a little bit of work with recognizing that, for example, an equilateral triangle has 60, 60, and 60 degree angles. But we're going to look at this a little bit more, and in some special cases, we're going to find out that we can actually determine side lengths if we know angle measures. And we're going to build the entire field of trigonometry out of this. So we're going to start off with what's referred to as the 45-45-90 triangle. Okay? A 45-45-90 triangle is half of a square. Okay? A square, of course, has equal side lengths. If you break it in half, the diagonals of squares bisect the angles. And so that 45-degree angle there will be formed above and below the diagonal. You have a 45 here and a 45 there. Okay? 45-45-90 right triangles, as they're called, are isosceles right triangles. You've got two 45-degree angles. You've got two equal sides because of the two equal angles. Okay, again, it's really just half of a square. All right? And there's some nice patterns that show up in side lengths of 45-45-90 triangles, and they come back to simplifying radicals. All right? So let's take a look here. Let's say that I had a square, and the square had side lengths of 2. So I chop that square in half. Of course, this side over here is also going to be 2. This is a 45-45-90 triangle. That's a 45-45-90 triangle. And I want to find the diagonal length of the 45-45-90 triangle. Okay? So the Pythagorean Theorem says I can take the leg squared, plus the leg squared, and I'm going to get the hypotenuse squared. Okay? That's going to be 8 equals x squared. The square root of x, in this case, is going to end up being radical 8. And the key here is seeing what happens when you simplify this down. The square root of 8 breaks up into the square root of 4 times the square root of 2. That diagonal ends up being 2 radical 2. Okay? So obviously there's no pattern here yet, but what we saw was I had legs of 2 and 2, and the hypotenuse was 2 radical 2. So I'm going to list that over here. So 2, 2, this side length is 2 radical 2. Okay? So there's one 45-45-90 triangle. All right? Let's do a square that's a 3 by 3 square. Okay, so a 3 by 3. So I've got a new 45-45-90 triangle here, a little isosceles right triangle. Okay? And I'm going to apply the Pythagorean Theorem. 3 squared plus 3 squared is equal to x squared. That's 9, that's 9. 18 is equal to x squared. Okay? So x is going to be the square root of 18. All right? If you simplify that down, 18 is 9 times 2. So that's the square root of 9 times the square root of 2. That's really going to be 3 radical 2. Okay? And now you might be seeing a bit of a pattern. We've got side lengths of 3 and 3 for an isosceles right triangle. Sometimes they'll just mark those two angles equal. You don't have to be told that they're 90 degrees. It's isosceles, so they're going to be equal. We've got side lengths of 3 and 3, and the hypotenuse is 3 radical 2. Okay? If we wanted to do this with a square of side lengths of 5 and 5, 5 squared plus 5 squared is equal to x squared, let's say. That's 50 equals x squared. X is the square root of 50. That's going to break up into the square root of 25 times the square root of 2. That's going to be 5 radical 2. Okay? I haven't really proved it necessarily, but hopefully you can see a pattern. We've got side lengths of 2, 2, and 2 radical 2. Side lengths of 3, 3, and 3 radical 2. And side lengths of 5, 5, and 5 radical 2. Okay? That's the pattern for a 45-45-90 right triangle. Okay? The legs get multiplied by radical 2 to give you the length of the hypotenuse. All right? So if I want to prove this, I can do it with variables. I could make this side x. I could make this side x. I call this side c, I guess. So that's a 45-45-90 triangle. Okay, it's an isosceles right triangle. We've got 2 equal legs. Okay, the Pythagorean Theorem says leg squared plus leg squared is equal to the hypotenuse squared. Okay, that's going to be 2x squared. I'm trying to find c, so take the square root of both sides. okay? So square root of c squared would just be c. And if you remember, when you break down a radical, you break it down into a perfect square times another number, all right? 2 is not a perfect square. X squared is a perfect square. This breaks down into the square root of x squared times the square root of 2 is equal to c. Well, the square root of x squared is just x. So that would give me x radical 2, and that's my missing side. So this pattern always holds. If you have a 45, 45, 90 right triangle, the leg multiplied by the square root of 2 is going to give you the hypotenuse. All right? So this can be very quick. This can be very easy if you know you have an isosceles right triangle and you want to try to apply this pattern. So if I have side lengths of 7 and 7 for an isosceles right triangle, you know the hypotenuse is going to be 7 radical 2. If I have side lengths of 20 and 20, hypotenuse is going to be 20 radical 2. All right? You can do it the other way around. If I have an isosceles right triangle, and I'm told I've got those 45-degree angles there, or that it's isosceles, say I have a side length of 12 radical 2. What got multiplied by radical 2 to be 12 radical 2? Well, 12. Those are going to be my 2 missing side lengths. So it can be really quick and it can be really easy. Okay? Here's where things get slightly tougher. You're not always going to have a radical 2 on one of those sides. You may have different patterns occurring. For example, they might give you a 45, 45, 90 triangle. Maybe you have a side length of 5 radical 3 and 5 radical 3. Okay? The pattern still holds. You're going to take the legs and you're going to multiply them by the square root of 2. Okay? You're just going to have to simplify it, and you may not get something that has a radical 2 at the end. So the leg of 5 radical 3 is going to get multiplied by radical 2. That's going to simplify down to be 5 radical 6. Remember, you can multiply numbers under radicals together. You can get new radicals. Okay? So if I have something like 2 radical 5, and it's an isosceles right triangle. First of all, you should notice, okay, 2 equal angles means we're going to have 2 equal sides. This is also going to be 2 radical 5. All right? According to the pattern, leg gets multiplied by radical 2 to give you the length of the hypotenuse. In this particular case, that would be 2 radical 10. Okay? Pretty straightforward. May not look like the pattern, but really that's what's happening. All right? Now, here's the other place where things can be a little bit tricky. I might give you something like 7 radical 6 for a side. That's the hypotenuse side. Okay? And you've got a 45, 45, 90 right triangle. You may have to go backwards to get the shorter side. Okay? So think about what happened here. This side got multiplied by the square root of 2 to give me this side here. This side got multiplied by the square root of 2 to give you 7 radical 6. What got multiplied by the square root of 2 to give you 7 radical 6? Well, think about it. Go backwards. Divide that hypotenuse by radical 2 to get from a long side back to a short side. Divide by the square root of 2. So 7 radical 6 divided by the square root of 2. A square root can divide into a square root. You're going to get 7 radical 3 as your missing side. That's 7 radical 3. That's 7 radical 3. And check. Okay? I can multiply 7 radical 3 by radical 2 to get 7 radical 6. Okay? So you multiply by radical 2 to get the hypotenuse. If you have the hypotenuse, you divide by radical 2 to get back to the shorter side. Okay? Now, one final example. The final type of example. These can get a little bit tougher. Let's say you don't have a radical at all. Okay? Let's say it's a 45, 45, 90 triangle. And they tell you this side length is 8. Okay? So this side got multiplied by the square root of 2 to be 8. Not 8 radical 2, just 8. Okay? So to get back to the short side, you're still going to divide by the square root of 2. Okay? You're going to take 8 and you're going to divide by the square root of 2. So 8 over the square root of 2 is going to be that side, and it's going to be that side. Okay? Remember, a radical can't divide into a whole number. And so as a result, you would need to simplify that down, okay? In another video, I'll try to talk about the idea of doing what's called rationalizing the denominator of a fraction, okay? Here's what rationalizing the denominator is. It's considered to be bad form to have a radical in the denominator of a fraction, okay? It's just not the best way to leave the fraction. If you remember, our concept is that you can square the denominator to get rid of the square root, okay? When you square something, you multiply it by itself, okay? It's a fraction. So if I multiply the bottom by the square root of 2, I've got to multiply the top by the square root of 2. I'm going to get 8 radical 2 on top. This is going to be radical 4 on the bottom. The square root of 4 is 2. And that should make sense, right? Because I'm squaring the square root of 2. Squaring the square root of 2 should just give me back 2, okay? If this whole number divides into that whole number, go ahead and divide it, okay? If it was 7 radical 2 and 2 doesn't go into 7, just leave it as a fraction. But if the whole number divides into the other whole number, divide it out. In this case, this is going to be 4 radical 2, okay? So this side is 4 radical 2, this side is 4 radical 2, okay? And again, it looks weird because we're expecting to see the radical 2 up here. But if you check the pattern still works, okay? The pattern is multiply this side by the square root of 2 to get this side, okay? And if you check, if you take 4 radical 2 and you multiply it by another radical 2, you're going to get 4 radical 4. But what's radical 4 equal to? It's equal to 2. And 4 times 2 is just equal to 8, okay? And you can see it checks out. So again, these can look kind of strange, and they can get uglier, okay? You know, you might see something that's not terrible. For example, if this side length is 10, again, this side got multiplied by radical 2 to be 10. So if you divide this side by the square root of 2, you'll get this other side. So that's 10 over the square root of 2, okay? It's a correct answer, but it's not formatted in the best form. We could rationalize the denominator, multiply the top and bottom by radical 2. You get 10 radical 2 over 2. 2 goes into 10 5 times. 5 radical 2 ends up being my missing side, okay? And again, we can check. 5 radical 2 times radical 2 will give you 5 times 2, which is 10, all right? They can get even uglier, okay? Let's say, for example, that I had something like, say I had 11. Okay, you would divide by the square root of 2 to get the other side. So 11 over square root of 2 would be the unsimplified answer. You multiply the top and the bottom by radical 2. You're going to get 11 radical 2 over 2. 2 doesn't divide into 11. I mean, you could say it's 5.5, but I wouldn't leave it in that form. If this number doesn't divide into that number, just leave it, okay? It's going to be 11 radical 2 over 2. If you had 2, you can write it as 5.5 radical 2. But I think that's the best form to leave it in, okay? They can get even worse, but the pattern is always the same. If you just kind of go with the pattern, things will work out. So for example, let's say this side was 4 radical 3. Okay, you still divide by radical 2 to get these other 2 sides. So you're going to take whatever this side is, divide by radical 2. Okay, it's correct, but it's not in the most simplified form. So multiply top and bottom by radical 2. You're going to get 4 radical 6 on top. You're going to get 2 on the bottom. Okay? You should check and see. Does 6 break down anymore? It doesn't. There's no perfect square that goes into 6. Does 2 go into 4? In this case, yes, it does. Okay? So you would get 2 radical 6 as your missing sides for this 45, 45, 90 triangle. All right? And it can get even worse. Okay? Probably about the worst kind of thing that you could see might be something like this. Maybe you've got something like 7 radical 3, and it's a 45, 45, 90 triangle. We want to divide everything by the square root of 2. Okay, so you get something like that. Multiply top and bottom by radical 2. Okay, you're going to get 7 radical 6 on top. On the bottom, you're going to get just 2. Okay, 2 doesn't go into 7. A whole number doesn't divide into a radical. Just leave it as 7 radical 6 over 2. Okay? So you're going to get some answers that don't look super simplified, but they're just fine in that form. That's what the back of the book is going to have. So hopefully that gives you kind of an idea about how 45, 45, 90 triangle patterns work.